In this video, we'll learn about the method of Lagrange multipliers, which is a nice tool to find the minimum or maximum of a function with some extra condition or constraint on your input values. So what we want to do is maximize or minimize some function of two variables such that the xy points are restricted or constrained by another function g of x and y being constant. So this could be a function that restricts x and y to the unit circle, let's say, and we are only looking at points on the unit circle and look points on the unit circle, what kind of function values will f give us on the unit circle and where it attains its maximum or a minimum. So to do that, what we have to realize is if we look at the level curves of a function, so these are the level curves of our function f. So this is just to illustrate the point. So let's say f is 5 along this curve. F is equal to 4 along this curve, 3 along this curve, 2 along this curve. And then we have this constraint given by g. And this constraint is a curve in the xy plane as well. So we are looking at the xy plane. And so we have this curve given by this constraint g of x and y is equal to k. Okay, so this is the level curve of the function g, this curve that we see here. And what we see from this drawing alone is along this curve g of x and y equals k, the function will be the function f will be maximum right there, and it will take the value 4. Okay, so that's the maximum right there. And what we also may recall from an earlier video is that the gradient vector of a function is always perpendicular to its level curve. So now if I draw the gradient vector of f at this point, I'm getting a vector something like this, and it points to the direction in which the function is growing the fastest. So it's perpendicular to the level curve. So this is let's give this point coordinates a and b. So this will be the gradient at AB. Okay, but similarly, if we look at the gradient vector of the function g, which giving us the constraint, this is also a level curve of g. So its gradient vector might point in the opposite direction, but still it has to be perpendicular to the level curve. So this would be the gradient vector of g at AB. The main point of this is these vectors might be of different length or point in the same or opposite direction, but the main point is that at a local maximum or a minimum of our function f along this level curve of g, these gradient vectors must be parallel to one another. So this gives us the method of Lagrange multipliers. So what we can say for sure is that the gradient of f at AB, the gradient vector of f at AB is a multiple of the gradient vector of G at AB. And this multiple, this number, is what's called a Lagrange multiplier. Okay, so the method of Lagrange multipliers basically consists of finding solutions to this equation of gradient vectors and keeping in mind that we have this restriction on the x and y values. Okay, so solving this equation of gradient vectors and respecting this constraint at the same time will give us the maximum or minimum of our function f along the level curve of G. Okay, so let me show you an example in the form of a question. So let's find the extreme maximum or minimum values of the function f of x and y, that is x squared plus 2y squared, along the unit circle. Okay, along the unit circle, which is the circle of radius 1 centered at the origin. Okay, so pause the video and choose your answer below. Okay, I hope you paused it and realized that, well, along the unit circle means that our function g of x and y is, in this case, is just x squared plus y squared. And the condition that we have to be along the unit circle is that g of x and y is equal to 1. Okay, so this k value is 1 in this case, and our function is given by that formula. So what we have to do now is look at this equation connecting the two gradient vectors. So write this equation for the gradient vector of f to be a multiple of the gradient vector of G. If we write these equations component by component, so the partial derivative of f with respect to x has to be a multiple of the partial derivative of g with respect to x. It's the same for the partial derivatives with respect to y, and also we have to keep in mind that g of x and y, that is x squared plus y squared, has to be equal to 1. So if we look at these equations, we should be able to solve for those x and y values that give us the local minimum and maximum. So let me just spell out those equations. So let me call this 1, 2, and 3, where 3 is quite obvious. Let's look at 1 and 2. So the partial derivative of f with respect to x is 2x. The partial derivative of g with respect to x is also 2x, but we have this Lagrange multiplier that is lambda. The partial derivative of f with respect to y is 4y, while the partial derivative of g with respect to y is only 2y. But again, we have this Lagrange multiplier. Okay, so these are equations 1 and 2. And third, we have to also make sure that x squared plus y squared, whatever solutions we may find, have to give us 1. Okay, so from equation 1, it's clear that either we have x equals 0 or lambda equals 1. These are the only possibilities to satisfy equation 1. If x is equal to 0, then equation 3 tells us that y has to be plus 1 or minus 1. Okay? So that's 2 points already. If lambda is equal to 1, then the second equation will tell us that y has to be 0, because we have 4y equals 2y if lambda is equal to 1. So the only possibility is that y itself has to be 0, and that when y itself is 0, then equation 3 will tell us that x has to be plus 1 or minus 1. Okay? So now we have 4 points. We have the points found here, which are x equals 0 and y equals 1 or y equals minus 1. And we have 2 points here, x equals 1 and y equals 0, or x equals minus 1 and y equals 0 are the 2 possibilities. So now we have found 4 points, and we can, these are either local minima or maxima for our function, and points that lie on the unit circle. So now if we evaluate the function at our original function at each of these points, we can see whether they are local minima or maxima. So let me just do them all in one go, well in pairs. So if x is equal to 0 and y is plus 1 or minus 1, then f is going to give us 0 plus 2, so that's 2. If x is equal to plus 1 or minus 1, but y is equal to 0, then f is going to give us 1 as the function value. So we see that these 2 points give us maxima, local maxima, and these 2 points give us local minima, such that they sit on the unit circle and maximize or minimize this function. Okay, so one more thing. Now if we would not look at the unit circle that we had before here, but instead we would look at the unit disk, meaning that what we have now is g of x and y be less than or equal to 1, so x squared plus y squared be less than or equal to 1, what we find then is that we still have these 4 points giving us these function values, but there will be a 5th one, so we are allowed to go inside and be in the interior of the unit disk. Then this function can be it can be shown that this function has a stationary point at the origin. Its first order partial derivatives both vanish at x equals 0, y equals 0, and it attains the value, takes the value 0 there. So if we look inside the unit disk instead of the unit circle, we look at the boundary of that disk on the circle using the Lagrange multipliers to find these 4 points, taking at which the function takes these 2 values, and then we look inside the unit circle in the disk to find a 5th stationary point, 5th point, where the function actually attains an even smaller value than on the boundary. Okay, so with this now we know how to compute constrained minimum and maximum values also on a curve or in a region as well. I hope you enjoyed this video, and I'll see you in the next one.